Okay, we're ready to talk about macroevolution. We've already been through some of the other evolution topics step by step, and we saw that there were different levels of the concept of evolution, starting with the first life form, then moving on to microevolution and changes within those life forms. Then we talked about survival of the fittest. Then we left off talking about speciation, about how it's proposed that new species can arrive from an existing lineage in there. Now macroevolution. Macroevolution is supposedly the result of repeated speciation events. The result of repeated speciation events. So speciation after speciation after speciation, supposedly these kinds of events led to more and more different kinds of organisms. We mentioned last time when we talked about the speciation process that it would be something that would be very difficult to replicate and do any kind of experimentation on. These events take thousands and thousands of years for enough difference to occur sometimes between these different populations for them to be considered separate species, no longer the same species. They would be reproductively isolated from one another. They wouldn't be able to interbreed any longer. So the result of repeated speciation events, one upon the other. Evidences for this. If we can't do the testing of a speciation event, if we can't evaluate it by experimentation, then it makes sense that macroevolution can't really be evaluated by experimentation either. So we have all these different kinds of evidences we look to that look to be the existing conditions that resulted from these long-term evolutionary changes. So, in our evidences, we're going to look at 4 different categories of evidences within the field of macroevolution. And the first one is comparative anatomy. Just by looking at the anatomy, of the different organisms and several different things we'll talk about having to do with comparative anatomy that lend evidence or support for the idea of macroevolutionary change. Along with that, we have the fossil record, paleontology. So we'll look at evidences in the fossil record that support the concept of macroevolution. Next, from biochemistry. The biochemical makeup of organisms can lead to evidences in support of this macroevolutionary condition. And then finally, from biogeography. So, you should know these 4 things are evidences that lead to or can support the idea of macroevolution, that concept. Again, remember, you can't test it outright. You can't reproduce things in the laboratory. We can't generate an experimental condition for this. We can only look at evidence as you find in these different areas here. All right, now we're going to look at evidences for evolution from the field of comparative anatomy. And the first type of evidence is what I call the congruence of anatomical characters. The congruence of anatomical characters. To be congruent means to line up with or be in agreement with. So when we look at anatomical features from one group to another, or one species to another, if they are from the same supposed ancestry, then we would expect that most of their anatomical features would be pretty much the same. If they appear more different, then we assume that they're probably not closely related organisms. They have a lot of differences piled up between them. So anyway, that's kind of, when we think of our own ancestry, we share traits that are common maybe with our parents and our siblings and so forth. So it's expected that based on our genetic information, we're going to have similarities in our genetic code. Therefore, we're going to be overall similar in many ways if we're closely related to somebody. In the same way, when we look at these animal phylogenies, those species that we assume to be closely related are going to look more similar. They're going to have a lot more similarities. Anatomically, they're going to be basically the same in a lot of respects. So you take, for example, cats. Cats is an easy example. We have tigers and lions and leopards and then the house cat and so forth. All those things. If we saw a species of cat that had never been seen before, we'd probably recognize it immediately as being some kind of cat. We know what a cat looks like. We have an idea of their overall features. And so anyway, internally, if we went in and we looked at the organization of their digestive system, their circulatory system, urinary and reproductive systems, and other tissues, the attachment of muscles, the shapes of their bones, there would be a lot of agreement. If we had a new species of cat, we would see that it was basically the same and had a lot of similarities to all the other cat species out there. So that's our first observation there. Shared features of two species which are derived from a common ancestry are expected to share many traits. And that's in fact what we find when we look at cats. We find all those similarities. And with any other taxon you want to think about out there. Might be the monitor lizards like the Komodo dragon and all of its relatives. They have basically a lot of the same kind of configurations in their skeletal and muscular and other organ systems in there. So the corollary of that would be that if two species are not from a shared ancestry, then there's no particular reason to expect that they have similar traits. So if you were to make the argument that wolves and coyotes are really not from the same ancestry, if they're not from the same ancestry, then there'd be no reason for them to share the same kind of circulatory systems, muscular attachments, skeletal features, and so on. There's no basis for that. They might look overall the same, a coyote and a wolf, but if they're not from a common ancestry, then maybe they would have a very different kind of internal anatomy, even though they might look the same from the outside. So anyway, this is what we're talking about when we talk about the congruence of anatomical characters. And this is a lot of what, when we think about Charles Darwin initiating a theory of evolution, he was seeing this, and he was looking at a lot of different kinds of groups of organisms, seeing similarities and differences, and noting these shared features between the different species. And anyway, so that kind of set up that kind of thinking leading toward Darwin's theory of evolution, the congruence of anatomical characters. Okay, our first evidence for evolution, for macroevolution from the field of comparative anatomy was the existence of congruent characters, in the anatomy of organisms. And our next idea is vestigial structures. Vestigial structures are anatomical features that are thought to be holdovers from some ancestral form of organism. They're no longer of any utility, or they're more trouble than they're worth, even maybe, in the existing species. So let's give a little definition to vestigial structures. Anatomical features which are passed down from ancestral forms which are of no utility or cause more harm than good. Now, commonly when we think about vestigial structures, some of the examples that are given are like our tonsils, because we often have to have our tonsils removed, or the appendix, have the appendix removed. Those are probably not very good examples, because tonsils do produce white blood cells. They're important in our lymphatic protection, keeping harmful bacteria and other microorganisms under control. So those white blood cells produced by those organs are useful. It's hard to say whether overall in the population if the tonsils do more harm than good, but I would say there's an argument there for them being more useful than trouble for most people. Same with the appendix. The appendix also has a lot of lymphatic tissue in it that can produce cells and antibodies that help defend us against disease. And so anyway, we also have muscles that will, on the side of our head, that are supposedly passed down from ancestral forms. That would be ear-moving muscles. That would move our ear, like a dog or a cat will move its ear, and other kinds of animals you're familiar with. Usually they have motility around their ear, and they can direct their ear one direction or another. But we can't do that. But we still have some of that musculature in our body. So that's an example of a vestigial structure in humans. So under examples, ear-moving muscles, in humans. In some other organisms, there are some better examples. For example, whale hip bones. Whales no longer have appendages, posterior appendages, no fins or flippers on the back part of their body. They have those in the front, but they don't have any toward the tail. So they don't have any hind limbs or any structures like that. But they still have the hip bone structure in there that would be supportive for any kind of hind limbs. So whale hip bones would be an example. Another example are the eyes of blind cavefish. They don't serve any purpose for a blind cavefish. They can't use them to navigate in their dark environment. And so usually these become to the point where they're no longer useful. Their anatomy begins to develop, and they have this vestigial set of eyes. So anyway, that's an example. So ears, ear-moving muscles in humans, whale hip bones, and eyes of blind cavefish are three of our examples for vestigial structures. You can probably think of many others, but those are some of those things. And they're thought to be evidences for evolution, because if they hadn't been passed down from an ancestry, we wouldn't have them. So things had changed from a time when they were useful in an ancestral form, they were a beneficial structure, but in modern forms, they're no longer of any utility or more harm than good. Now we're going to talk about our third evidence for macroevolution from the field of comparative anatomy. We've already talked about the congruence of anatomical features and vestigial structures. Now, homologous structures. Homologous structures are features that we think develop from the same embryonic kind of origin. They have the same structural origin, but as an animal develops, they become expressed in vastly different ways in different kinds of organisms. So, anatomical features which have the same developmental origins but may be quite different in their final expression, their final anatomical form. One of the more common examples we use here is the forelimb of vertebrate organisms. So in humans, we're familiar with the normal upper arm, forearm, the hand, the five-finger arrangement, and that basic arrangement is fairly common through most vertebrate organisms. You'll see it in frogs and lizards and crocodiles and turtles and all kinds of mammals. Most all mammals have that basic arrangement, and you'll see some modifications of that in different groups. So you'll see the loss of digits or limbs in some of the reptiles. Of course, snakes don't have any limbs. Some of the lizards have a much reduced, a much smaller kind of limb. The caecilian amphibians lack limbs. The Amphiuma salamander looks more like an eel, has very, very tiny legs and may only have like 2 or 3 toes on the end of the limb. So anyway, there's some variation in those groups. Some more extreme examples of variation of the limb would be like in the wings that are formed in a bat or a bird. So it looks very different from our arm and hand arrangement when it forms a wing. And the flipper of a whale also would look quite different. So those are some variations that you see. The hoofed animals have a fusion of their digits and either one or just a few toes, 1, 2, or 3 toes to stand on at the end of their foot. So anyway, these are examples of homologous structures. They all start from a limb bud in the embryo, and then as they develop, they look quite different. A lot of other things would be this way as well. The kinds of tongues that animals have. There's a lot of variation in the tongue arrangement, teeth arrangements as well. So you'll see them start basically the same, but they can end up looking quite different. The existence of the tail, how the tail is expressed in different organisms, and so on. So there are a lot of different variations you see on these basic embryological structures that start to form an organ. So we consider these homologous structures. They're similar in form. A couple of related terms we need to bring up here. The term analogous means it's the same in its overall appearance, so that the wing of a bat and the wing of a bird have the same kind of general appearance, but they're not thought to be from the same ancestral kind of origin. So they're analogs. Same might be true even of a wing of some insects, like a dragonfly or something like that. It's basically something that sticks out to the side of a fin of a fish, a similar kind of thing, analogous. That wing-like appearance that forms on some fish. So that just means that they look the same. If they look the same, they're analogous, similar in their appearance and function. If they look the same, but they do not come from a similar origin, they're not from the same ancestry that formed that, then it's considered a homoplastic trait, homoplasy. So those are two terms you need to be familiar with: analogous and homoplastic. Now, they can be analogous, they can look the same, and if they come from the same kind of ancestral lineage, supposedly in the evolutionary line, the things would be homologous, okay? So analogous traits can be homologous, they come the same way, but if they come about in different ways, we call that homoplasy. Homoplasy. Now, for another kind of evidence from the field of comparative anatomy that supports the concept of macroevolution, this is intermediate forms, the existence of intermediate forms. It's any species or taxon taxa. So when we're thinking of this, we're thinking of the phylogenetic chart, and we have one group of organisms in here and another group over here that are very different in a lot of different ways, and then we find there's another group that is more similar possibly to what their ancestral form that they both had in common may have been. So I'm going to use the example of Polypterus again. So Polypterus kind of is similar if we look at our phylogenetic chart, and we'll look at this again later. If we look at our chondrichthyan fish over here, chondrichthyes are shark, skates, rays, and ratfish, all those over here on this lineage, over in this way. And up this direction, we're going toward bony fish, all of the modern bony fish. So we have our ray-finned fishes and our lobe-finned fishes. So ray-finned fishes up here. Our Polypterus would be most similar, the most similar link between chondrichthyan fish and ray-finned fishes. So here's where Polypterus is. It's down here near this point of separation, but it's a separate branch coming up along the ray-finned fish lineage in there, also close to where the sarcopterygians, the lobe-finned fishes, would be. So it has features that are common to lobe-finned fishes, features that are common to chondrichthyes, and some features that are common to the ray-finned fishes. So it's a small little group of fish that seem to be more similar to that ancestral type. So a taxon that has anatomical features which link to other more dissimilar taxa. So the presence of these in here gives evidence that there was maybe some ancestral form that gave rise to these other groups, because we have an example that's very similar to something that might have been like that. So this is what we consider an intermediate form. Sometimes when you hear people talking about discovering some form that seems to be very ancient or ancestral linking modern forms, they call it a missing link. It's no longer missing after you find it, but they found some missing link between things. I generally reserve that term missing link to fossil forms rather than living forms. But these are living intermediate forms that serve to bridge this gap in here. Our fifth area from comparative anatomy that supports this idea of macroevolutionary change is something we've already mentioned earlier on when we talked about the relationship between developmental processes and the phylogeny of a group. Von Baer's law. Features common to all members of a major phylogenetic group of animals develop earlier in ontogeny than features that distinguish subdivisions of the group. So we're already aware of that those features like having, for vertebrates, a backbone, right? All the vertebrae in there, and before that, even a notochord. So the notochord is common to all these chordates, the pharyngeal arrangement of supports around the pharynx. That's common to all of these groups. So those kinds of things develop early on. the things that make the different groups more different from one another, like epidermal scales and amniotic egg and the reptilian group, separate that from the amphibian. So that kind of feature would develop later in the embryology and the embryonic development of the organism, later in ontogeny. So anyway, von Baer's law, another area that supports the idea that there was common ancestry, that they had a common origin in these different groups that we're talking about. So those are the areas from the field of comparative anatomy that support the idea of macroevolution. Next, we're going to look at evidences from the fossil record.